Yeah. So for us, the language that I wanted you to become proficient in was Python, and we stuck only to Python in this course, although some of you may go on later and study Java. A lot of you won't, so there's no point in really doing this sort of crash course in Java. The good thing is, though, that the basics, at least in Python, are about the same as in pretty much every other sort of normal programming language. There's a few bizarre ones, types of languages that you'll study in, for example, Comp 3007, if you ever take that, which is about programming paradigms. But most of them, the lessons that you learn here today carry over perfectly. In fact, Python is nice because it's really one of the simplest languages, so that everything that Python does, other languages do. Sometimes it's more complicated or difficult to accomplish in other languages. So what are the sort of basics? Well, basic constructs in Python and everywhere else are things like variables. So we saw in Python it's very easy to create variables. You just assign some value. You pick a name and you assign it some value, and suddenly you have this variable. We saw that there's this notion of scope of variables, that when you define a variable inside a function, then that variable really only lives as long as the function is executing. When the function leaves, the variable is gone, meaning so that's called scope. The variable is no longer in scope. And in Python, that's really the main property of variables is scope. In other languages, variables have other properties. In particular, they often, in type languages, they have types. So when you declare a variable in some other language, you have to specify beforehand what kind of variable it is, what kind of thing it's going to store. In Python, they're all the same. Okay. We saw functions. So it's very easy to define a function in Python. Again, there's almost no code involved. The keyword def is the thing that generally tells you you're defining a function, and the name of the function and its list of arguments, and away you go. So that's sort of something that you're going to find in every, let's say, normal programming language. We saw operators. So all of these arithmetic operators, for example, but in addition to arithmetic operators, we also saw that depending on the type of variables you have or the type of data you're using them on, sometimes they mean different things. So, things like string concatenation. So that's plus. Even though plus, if you give it numbers, it gives you back. And somehow even things that take two different kinds of arguments, like, for example, the multiplication of a string by an integer gives you a string. Okay. So that's a sort of important thing. And a critical thing there is order of operations. And order of operations is, that's this thing that we defined as BEDMAS, or we called BEDMAS, plus some other stuff, because in addition to brackets, exponentiation, division, multiplication, addition, and subtraction, we also had logical operators and comparison operators that also squeezed into those things. In some sense, these are a necessary part of programming languages if you want to be able to have code that's readable. On the other side, they're not my favorite thing because they, again, require some kind of memorization rather than understanding. So for most of us, it's not difficult because we've been studying mathematics for so long that we remember things like multiplication has a higher order of precedence than addition. And when you put brackets around things, that changes this order of operations. And even exponentiation, we sort of know that that's more than division and multiplication. But as the list of kinds of operations gets longer, you have to keep remembering where they fit into this thing. So yeah, that's something you get used to, but it's sort of not my favorite thing because it's just rote memory work. You don't really need to understand it. You just need to know it because there is no understanding it. It's just our choice of conventions. So we had comparisons and logical operators in there as well. So at any time, stop me and ask me a question if any of these topics is you were confused by any of these topics, and I'll do my best to answer it. We learned about data types, and first we saw numerical data types. So those were things like, well, we can even split them up finer. With numerical data types, we had integer and float. And we saw that those things are quite different. So integers, they're sort of the things that we normally dealt with since we were children and we started learning to count. You do arithmetic on them, and every answer that you get is exact. There's no problems there. Everything works great. And then we saw these floating point numbers that you would learn about later in life, or they correspond to the real numbers in mathematics that you learn about later in life. The difference is that in mathematics, real numbers are, again, when you do computations on them, they give you exact results. So you can do things, sort of mathematically, like prove that this equation, this formula on this side is equal to this formula on that side by doing operations on real numbers, that if you do the same thing, the equivalent thing in Python using floating point numbers, those two things may not be equal. And we saw really trivial examples like, I think in the first class we did something like 0.3 minus 0.1, and we didn't get 0.2. So little mistakes that happen in floating point numbers that make them less than ideal for some applications. All right. We saw string data. So those are sequences of characters, usually to represent text in a program. We saw arrays or lists. Again, sequences of things, not necessarily characters now. They were this sort of main way for us to store variable amounts of data. So when you don't know how much data you have, your program is going to handle, then usually you have a list that stores it. Or if you have a function, you don't know how many arguments it can take, or there's no fixed upper bound on the number of arguments to it. Well, then you don't really make a function with an unlimited number of arguments. You make a function that takes a list as an argument. So examples of things like functions that compute the sum of all the elements in a list, that kind of thing. Okay, so that's how we started out, and I think that that got us through the first week and the first assignment. In fact, the functions in the first assignment, although you defined them because that's what the assignment asked you to do, there was no real interaction between them. And so then the things that you were creating using these constructs are basically what's called straight line code. These are just things where you maybe define some variables, you do some operations on those variables, and you return a value based on some computation. The sort of thing that was not present in any of that is any idea of branching or looping. And so that's what came next, were if, elif, and else statements. So those are what are called branching constructs, because really what happens is the flow of control when you hit an if statement takes a branch. Either you can skip over it if the condition is false, or you can do the block of code associated with that statement if the condition is true. So that's called a branch. And you have if and else, and there's a sort of common occurrence where there's a bunch of different possible cases, mutually exclusive, that can happen, and that's where this elif is helpful. So you have if, a whole bunch of elifs, and then a final else, and then you know that exactly one of those things will get executed anytime you go through it. And then we had looping constructs. There were basically two kinds of loops. For loops. So that is basically iterating over some, let's say, fixed list or sequence. So for example, arrange was a really common one. That's the sort of classic for loop where you have a variable that counts 0, 1, 2, 3, 4, 5 up to n minus 1. Or you can iterate over any sequence. For example, the values in a list also works. And then there's another kind of loop, which was the while loop. And the while loop is really the most interesting one of all of these constructs, because although we didn't really do anything with it, but it's a fun exercise to play, you don't need anything other than while loops. So I think it would not be hard at this point in the course for you guys to realize that for loops, they're convenient and they're handy, but we don't really need them, right? Because you can write a while loop that does exactly the same thing as a for loop. That's not a difficult task. Perhaps you may be a little bit more surprised to realize that, well, actually, if you're really a purist, you don't even need if, else if, and else, because you can do any of those things with a while loop also. It's awkward, but it's certainly doable. I mean, you just make while loops that only execute 0 or 1 times. That's basically what an if statement is, right? An if statement is a block of code that executes 0 or 1 times, depending on the value of a condition. You can craft a while loop that does the same thing, and all of these other things, if and else if, well, they're just sort of convenient, but not strictly necessary. So, as a kind of thought-provoking exercise, you can think of, well, how could I write every program that I ever wanted to write just using while loops? Not too difficult. Okay. So this is what I would classify as basic constructs, and pretty much universal in the sense that they are present in all the major programming languages or all the major procedural programming languages. So going back even to the 1950s, you would see programming languages that that had equivalents roughly of all of these things. And then we had some more I'll say specialized or advanced constructs. So one of those things was exception handling. We saw that you can use try and except when you have a block of code that something may go wrong in. You can wrap it up in one of these things, and if something does go wrong, you can catch it with this except. So if the user enters the wrong thing, or the user gives you something that's supposed to be a number, and turns out that they don't do that, then when you try and convert it to a number, you get some exception happening. This is a way to handle that, to sort of deal with that when it happens, so that your program doesn't execute. You can just deal with it in some graceful way, typically like asking the user to enter the number again. We also saw objects. So these are not available in every language, but more and more languages have them. And even before there was such a thing as object-oriented programming, there were something similar to objects, which we might call compound data types. So some languages which don't quite have objects still have what are called compound data types, or structures that are things that have parts that have names. So the difference between those and objects is objects have data, and the data has individual names, like a point might have an X and a Y variable associated with it. But objects also have functions that operate on them. In some other languages, they don't have such things. That objects are just or they're not objects. They're structures or compound data types. They're just pieces of data. You have to operate on them externally. So in there, you've also got objects have properties, but those are just variables, pieces of data that are local to them. They also have methods. Those are just functions that operate on the object. We saw how to define those. And one of the things that I want to show you today is that objects also have this notion of inheritance. So a good object-oriented programming language will have some notion of inheritance. These are things that you might call superclasses and subclasses. And I'd like to just give you a quick example. So let's define a class called person that has an init method that takes a first name and a last name. And like most of these init methods, it just stores its arguments, or many of these init methods anyway. And maybe it also has a way of turning itself into a string, which is just to return the first name concatenated with the last name. So there's an example of using that thing. And if I print p, well, the print method converts it to a string, and I see it look like that. But if I just inspect p, I see it's some object. Okay. So we can imagine many, many applications where we might be keeping track of persons, but maybe there's special kinds of persons as well. So, for example, in something like a payroll application, you may have something like an employee. So, is an employee different than a person? Is it the same thing? Is every person an employee? Is every employee a person? What of those things fit? So is every person an employee? No. I imagine there's many people in this room who are not employees of anyone at the moment. Is every employee a person? Usually, unless we have some, let's say, non-human employees. So we can capture that. So there's this, even in the way we talk about it, we can say every employee is a person. And that is a clue to us that, well, there's some relation between these two kinds of objects, and it's this is a relation, and in object-oriented languages, that's represented as one thing being a superclass of another. So in this case, a person is a superclass of employee, or if you like, a employee is a subclass of person. So an employee is a kind of person, a special kind of person. Okay. And so I think I can save that. Let's not do that. So maybe an employee has, like a person, they have a first name and a last name, but maybe they also have an employee number. So what we've got is an employee is a special kind of person, and persons already know how to sort of take care of themselves, how to initialize themselves, so we want to use that. So we do, what was it? I think it's just super. We do the following. First name, last name. And let's see if that works. So employee should have a first name, a last name, and a number. Maybe something like that. Okay, so that creates an employee. Let's save it. And if we print it, we see that it prints Pat Morin. Okay? Which may or may not surprise you, but the reason it should maybe surprise you is if you look at the employee class, there's no string method there. So somehow employees know how to turn themselves into strings in a meaningful way, and how do they know that? Well, they know that because every employee is a person, and every person knows how to convert themselves to a string. So the real advantage of this relationship of making something a subclass of something else is that subclass, in this case employee, can immediately do everything that the superclass can do. In this case, it can print itself. You don't have to write the code twice for that. If you want employees to print themselves the same way that persons do, you just don't do anything, and that happens by default. Okay. Is that clear? All right. So, any immediate, obvious question there? So you might say, well, what if I'm not happy about the way an employee, what if I don't want them to print themselves or turn themselves into strings the same way that persons do? What would I do in that case? Maybe when I look at an employee, maybe I want to see, actually I don't care about their name, I just care about their employee number. So what would I do in that case? Yep.
Not call the super method and make a string method for the self.number?
Well, we're not calling the string method anywhere in this code. So this thing here is a funny bit of code that calls the superclass's init method. So it says, look at my parent class, which is person, and call their init method with these two arguments, fn and ln, short for first name and last name. So that ends up calling this method up here. Okay. But the string method we never called or anything. What happens is when Python wants to run a method on something, when it wants to call something string method, it first looks to see if employee has a string method, and it doesn't. So in this case, it looks in its parent and sees that person does have a string method, so it uses that one. So if you wanted to change the employee string method, you just redefine it. So you say just do something like that. And now if I look at E, it's just a number. So if you're not happy with what you receive from your parent, then you can just override it. And so that's called overriding it. It just means you decide how you do it. And if you are somehow all you want to do is what your parent does and more, then you can even use your parent's code, and that looks something like this. You do a super. I think this should work. So in this example, I mean, you could imagine that the parent code was more complicated than in this simple example, so we wouldn't want to copy it all and redo it ourselves. We just call it this way, saying do whatever my parent does, but then also append, in this case, my employee number to the end. And that's how I get something like this. Okay. So that's the notion of inheritance. And I can do this arbitrarily now. You know, I can have a subclass of employee called HR employee, or a subclass of employee called faculty member, or a subclass called, I don't know, gym employee, whatever you want. You can build these, what they're called inheritance hierarchies, and how to choose these things and how to design them. They're sort of a big topic in computer science. It's basically a large part of software engineering is the design of class hierarchies. But you'll learn more about that in the future. The only other thing that I would like to mention about this right now is there's something that people like to talk about in object-oriented circles, and you may hear it, and that is this notion of what's called polymorphism. And so poly means many, and morph means shape or form. And so what polymorphism basically is about is having pieces of code that take things of many different shapes. So, for example, it's somehow so common, we've been doing it all the time, but maybe never realized it, because it just happens always in Python. And in type languages, it's a bit more of a big deal, but it's very easy for me to write functions that accept different kinds of arguments, and they work for different kinds of arguments. So, for example, here's a function called show somebody that takes an argument that is a person and prints them with some stars around it. Okay. Now, it doesn't matter if I pass that thing an employee or a person. So now I have these two things, this employee and this person. But that show somebody function is happy to take this person, and it's happy to take this employee. Works for either of them. That's a notion that in the object-oriented programming circles is called polymorphism. It just means that I've written a function here which can take things that have different shapes, meaning they are different classes, but they'll work for all of them. The only thing that I have to make, the only sort of requirement is that whatever I do inside that function should have a meaningful interpretation for every kind of object that I expect it to work for. In Python, converting something to a string is actually something you can do to any object, and so this is a function that actually works with anything in Python, and we did lots of those. But you can imagine other cases where this function might only work for persons because persons have a special function in them that only works for them. So for example, I could say something like this. So I can say, show somebody P, I see their first name. Show somebody E, I see their first name. But if I say X is 23 and try and show somebody X, then of course that doesn't work because X is an integer, it doesn't have a first name. Okay. So that's the idea of polymorphism. Okay, so we had inheritance, classes and inheritance, and polymorphism. Okay, all right, so that's kind of like the language. That's Python, the language that we've learned so far. Does anybody have questions for me about any of that? Yeah. So as an argument where? Like here? Like this kind of argument? So this is a lowercase p, so this is just a variable name. So I could, call this x. Maybe that makes things less confusing. This is a function that takes some argument. It's called x, but in this case, I've written it so that it really requires that x have an attribute called first name, and in this particular small example, every person has a first name, but maybe other types of objects don't. In other type languages, that's more of a big deal because in addition to saying that you take an argument called x, you'd have to say what kind of thing x is supposed to be, and then you might say, okay, well, x is supposed to be a person, in which case I'm guaranteed that it has a first name, so this would be a safe kind of code. On the other hand, if I said, even if I said employee, I'd still be guaranteed that it has a first name. Okay. So any questions about any of this stuff about the language? So, how do you guys feel about your proficiency in Python? Are you comfortable with the language? No? Ish? More comfortable than when you started? If, you had some small, small data processing task, let's say, that you needed to do that was just like too big to do by hand. So I don't know, somebody gives you a book that's like 2 million words long and they want to know something about the book that you can't quite get just from your text editor using find and replace or something. But I don't know, there's something like counting how many times the word the appears, or the words the and, or any article or something appears. Is that something that you could consider tackling with Python these days? Yes? No? Okay. So if that sort of thing still scares you, that's okay. But what I recommend is keep your eye out for little problems like that creep up for you, and really consider, okay, maybe I can solve this thing using Python. I can sort of brush off my skills and do this again. It'll both act as a reminder and maybe help you understand how really useful these things can be if you know your way around them a little bit. I mean, this is really the kind of thing that if there's not a lot of programmers around where you work and you can do even these simple programming tasks, you can really impress the people around you. Although then maybe they'll come and ask you for help all the time, so you may not want that. Okay, but that's the language. Basically, there's not too much more about Python that we learned. After this, everything is somehow more general lessons. So another sort of big lesson was learning how to solve computational problems. So coming up with a solution and breaking it down into steps. So that's sort of the thing you have to do as a programmer, because these programming languages, they only have small things to use, right? You look at all the stuff that we listed here that Python can do. It has some basic constructs and some functions and some really simple data types, branching and looping. It doesn't have any big things like that just solve problems for you. I know that that's kind of the dream nowadays of what's happening with machine learning, is you'll just tell your machine to solve this class of problem for you and it'll do it. But we're not there, and we're not even close to there yet. So that really we're still at the state that, when someone wants to solve some problem, and even if that problem is just, read a number from the user and multiply it by 2, we have to think about how to break that down into steps. How do we read a number from the user? Okay, well, that's with the input function in Python. How do we multiply it by 2? Well, that's with the multiplication operator. Well, we probably meant not only multiply it by 2, but also maybe print the result. Okay, so that's a print statement in Python. So we really have to think about these things one step at a time. So that's the most fundamental thing that we learn here, is things that we just somehow think are trivial because you just say what to do. I mean, you could explain this to a child, what they should be doing, but explaining it to a computer is even more time consuming than explaining it to a child, because you have to be completely precise, and the computer is going to do exactly what you told it to do, even if that's not what you meant for it to do. So that's sort of an important thing. And on a bigger scheme, here are some of the techniques that I've tried to teach you. First one is straight line programs. So you may remember your first few assignments, certainly the first one and a chunk of the second one, they were just programs that say you solve them by just a bunch of lines of codes that execute one after the other, and then the solution gets printed. So things like the BMI calculation. There was no branching really there or anything. You get a number from the user, you apply a formula, and then you print the number that comes out of that formula. A little more complicated were things like maybe the BMI thing that actually tells you what category your BMI is in. It's the same program, except at the end there's an if statement or an if-else statement that classifies you into one of these 3 or 4 categories. So those are sort of straight line programs. From the question, the answer is fairly clear. It's just one thing after another. Sort of another kind of thing, sort of solution is iterating over lists or arrays, and many variations on this. So sometimes you have a whole pile of data and you want to pick out only the interesting stuff. So, you know, this was this example of crime in Denver where you have just an enormous bunch of crime records, or records of police interventions, I guess. And it's just too big to pour through on your own, but you might still be interested in asking some questions about it. And the way you ask those questions is basically you say what you're interested in, and then you go, or let the computer go through that list looking for the things that match your criteria. There's lots of things like that. Or maybe it's not going to actually return a list of all the things that match your criteria. Maybe it'll just count them for you. But in both cases, the way it does it is just by going through that list, looking for the things that are relevant. Okay. So that's sort of the more basic types of things. And I would say that right now in the world these days, a huge amount of what happens and what's done is exactly solved by this process of iterating over lists and arrays. There are whole programming paradigms based around ways of writing this iteration over lists and arrays that allow it to become distributed or spread out. So, for example, places like Amazon that have billions and billions of pieces of information about customer data, they work. A lot of the things that they do are exactly that. What they want to know is, out of all of the billions of pieces of customer data that they have, what are the ones that match this criteria, or how many match this criteria? And that actually becomes very sophisticated at their level, but ultimately the solutions that they're implementing are basically what we could do in this course. The difficulty for them is that data is spread out over a bunch of servers all over the place. Iterating over them one at a time would be too slow, so they want to distribute that computation, but ultimately that's all it is iteration over some enormous list. Okay. But sometimes we can be a little bit more clever and solve things a little bit faster. So one of the techniques that actually you came up with this in this course is binary search. So we, in the second or third week, we started making our first games in this course, and the first game that I made was a guessing game where the computer picks a number between 1 and 1,000, and your job is to make repeated guesses at it, and it tells you whether your guess was too high or too low. And everybody seemed to figure out how we could solve this thing and what was the right thing to do. So what was the right first guess in that game? The middle. Okay? So, and the middle, because no matter what the thing tells you, you know that after you've guessed that, you'll only have 500 options left. So you started with 1,000 and you made one guess, and now you only have 500 options left. And you keep doing this. After 2 guesses, you only have 250 options left. After 3 guesses, you only have 125 options left. After 4 guesses, you only have 67, 68 options left, and so on. And what we saw is actually you can beat this game every time if you're allowed to have 10 guesses. And so you guys, I mean, it's a very natural thing. You guys discovered it. It's binary search. And this is something that you can find something in a pile of size n using only log n guesses or sort of peaks. And so it's really useful in sorted arrays. And it's a really general and powerful sort of algorithmic design strategy. And anytime you can make a guess and cut the amount of options in half with that guess, then you win, and you can apply some variant of binary search. Okay. That's good. Something we sort of did on the most recent assignment, and we've used it a few times before in the course, is sorting, or basically problems that become easier after sorting. So these are things like this min gap problem that we looked at. Although we have a nicer way of doing it in Python, finding duplicates is also one of these problems that becomes really easy if you sort, because if you have a list of things and you want to know if there's any duplicates in there, well, you can sort them, and if there's any duplicates, then they're going to appear side by side in sorted order. So you can sort and scan. In Python, we have a nicer, better way of finding duplicates, which is to use sets, but those aren't available in every language. We've seen problems that become easy using sets and dictionaries. And a few of those were removing duplicates, so getting all the unique elements. What else? A neat application was finding, they were anagrams. So we saw that using a dictionary you can find the list of all English anagrams very quickly. Frequency counting is another one. If you want to know how often various words appear in a text, you can use a dictionary for that keeps track of the number of times you've seen each word. All of those things. And yeah, then those are just some basic things to try if you're faced with some computational problems. Think about these different approaches before you just jump in and start coding. Maybe one of them works for you, and a sort of last resort is brute force, and that's where you try every possibility. Like if someone asks you, does your list contain a pair of elements that add up to, it's a list of numbers. Is there a pair in there that adds up to 50? Well, the brute force approach would be to just try every pair of numbers and see if you add them together if you get 50. It's not the approach that I would recommend, but it's one that you don't have to think too hard about. The only thing that you need to work out is some way of listing out all of the possible pairs, but that's not too hard to do with 2 for loops, because you can, for example, have a for loop where I runs from 0 up to the length of the array minus 2, and where inside of that one in which j runs from I plus 1 up to the length of the array minus 1, and then you can convince yourself that will have tried every possible pair ij of indices in your list. sometimes the brute force approach is a nice way to do a first try at something without having to really understand too much about the problem. Okay. Another sort of learning objective here was learn to do a, let's say, medium scale project using a third-party library. Okay. So that's something that's, third-party library here means something that's not part of basic Python, something that comes from somewhere else. And medium scale here means something that you could do over the course of a week or two on your own. And that project was your Pygame game. So that's a reasonable sized project. There was a good number of requirements to do there. Leading up to it, you had to learn how to use this third-party library that was quite different from, let's say, all the stuff that's in the normal Python libraries. And you know, at the end of it, some of you did some really nice games, and really, you know, accomplished something substantial, and that's good. Hopefully, that's gives some confidence for you guys to tackle bigger projects in the future, or even smaller projects, but ones that you're doing without any sort of guidance. A side effect, and another reason that we use Pygame, is to learn about event-driven programming. So the whole model of things in Pygame is you set up your game, and then you wait for things to happen. Either the clock ticks and it's time to do a refresh, or someone clicks the mouse, or any number of things happens. But the whole model of event-driven programming is exactly that. Your program is not something that's running all the time, spinning away, working furiously. Most of the time, and this is true of most applications, and it's true of basically most computers nowadays, mostly they sit around doing nothing except waiting for us, the very, very slow users, to tell them to do something. Right? There's a reason that, you know, your phone battery can last for a day and a half, is because mostly the processor in your phone is not doing anything. It's just waiting for you to click something. If you ever use a phone furiously, you'll realize that actually the battery only lasts a few hours if you're truly using it. And by truly using it, I mean computing something on it, not even using the user interface. Remember that this computer is working in billions of cycles per second. You even typing as fast as you can is not even coming close to using that thing at all. Mostly it's just waiting for you to press another key. So it's a really important thing to know this event-driven programming, because pretty much everything is doing that. Even the servers at Google, mostly they're sitting around waiting for people to enter queries so that they can go and search for them and send back the results. Most of the time they're just sitting there waiting. I mean, it takes them a fraction of a second for every one of these queries. And it's good that they're sitting there waiting, because it means we get our answers back quickly when we type them in. But of course they shouldn't be spinning away doing something all the time, because they would be eating up all the electricity in the world if they were. Okay, so that was the lesson from Pygame again. A sort of big computer science lesson is learning about recursion. So you had an assignment on this, and we did examples in class. So this is a big lesson in computer science. and in mathematics, about expressing solutions to things in terms of sort of smaller instances of the same things. In mathematics, that's called mathematical induction, and in programming, it's called recursion. And there were basically two pieces to these puzzles, which are the base cases. So when is the problem so small that it's easy? We know the answer immediately. And the recursive step. So that's something like reducing to smaller instances. And we saw examples of things like the factorial function that you can define recursively. That's sort of an easy one. We did some sort of learning things where we added up the elements in an array using recursive functions. Sort of also easy stuff. But we also looked at some sorting algorithms. And those were kind of cool because I think most of you here had never seen how it is that a computer sorts a list of numbers. And I showed you Quicksort, which is this really simple recursive sorting algorithm. And even after seeing it, I think most of us still didn't know how it is that a computer sorts a list of numbers, even though we just saw it. That was like the first example that really shows the power of recursion, because it really felt like we didn't even understand what we were doing, yet somehow it did this very complicated task of sorting these things. Just because we let go and we relied on the fact that it would correctly solve the smaller problems, and all we had to do was put them back together. In fact, for Quicksort, all we had to do was break it into two smaller problems, and then it was essentially done. Okay, and lots of things. Once you get used to recursion, it becomes kind of a natural tool to use, and lots of problems lend themselves to easy to explain and very efficient recursive solutions. We looked a little bit at analyzing recursive algorithms, and we saw that it's extremely difficult, or it seems to be quite difficult until we develop some more mathematical techniques. I would say that basically the only tool we have right now is to look at the recursion tree and try and understand what's going on there. Okay. Another thing we learned about in recursion was what these stack frames are and how they appear and then disappear as functions are called and they return. And that ties in with something away from the top of this course, which was variables in scope. So we somehow learned that variables have scope and they only live within certain functions. And that became really important when we did recursion, because we really needed to understand that when you call the same function twice, each call to that function has its own copy of all of the variables that the function is using, and only one of those is in scope at any given time. It's the function that's the instance that's currently executing, and it takes some mental power to keep track of all of these things that are going on here. And then it's important to really understand scope and the way these stack frames work. Other than that, I would say that we learned a really little bit about efficiency. And I'll say only really a little bit that maybe we learned the difference between log n, so those are things like binary search, constant, those are things like just doing basic arithmetic. Linear, that's something like iterating over a list. So let's say a list of length n. And we saw through some sort of bad examples of quadratic time things, and these were like iterating over a list of length n and iterating over the same list during each iteration. So we saw that that's a very easy thing to end up doing, and the classic example, it showed up on the midterm, was something like so it's very easy to do in Python without even realizing you're doing it. Give me a big list of words, and I ask you for all of the words where the reverse of that word also appears in the list. That's actually exactly this model of iterating over a list of length n, right? That's what's happening here for w in words. And what's sort of hiding in here is for each element you iterate over, you're actually iterating over the whole list again, because the way Python internally checks if this thing is in the list of words is to walk through the whole list of words again, looking for that thing. So that gives this quadratic sort of performance, meaning that if the list has length, let's say 100,000, then the number of sort of basic operations that are happening is 100,000 times 100,000, and so that's over 10 billion. Yeah, even more than that. And we saw that takes a minute or two to finish, whereas if we did it a little more carefully, it would only take a fraction of a second. Okay. We didn't do too much more sort of analysis of performance in this this course. We kind of left it at there. Okay, so those were our objectives, or at least the objectives that we got to in this course. I don't have anything more to tell you today. Does anybody have any questions for me? Yeah.
There were 2 questions about secret classes on the 2012 midterm.
Yes.
Can you go over them?
Sure. Let's see. Really? There we go. Okay, so in these questions, there was this following class hierarchy. We had a person class that had a first name and a last name. It had an equals method defined, and it had a string method defined. And here I created two persons. One is assigned to the variable PM1, and the other one is assigned to the variable PM2, and they both happen to have the same first name and last name. So if I ask, does PM1 equal PM2? So what exactly happens then? It returns true, and why does it return true? Okay, but when it compares the value of both, what happens? Where is that being done? Yeah. So this person class defines an EQ method. So if I say, does PM1 equal PM2? PM1 is a person. So Python uses the EQ method in that class. And if you look at that EQ method, well, it compares the first name and the last name, and if those two are both the same, then it returns true. So this will return true because these two persons happen to have the same first name and last name, even though they're different things in different places in memory. Now, if I ask, does PM1 is PM2? That's asking Python, do these two things live in the same place in memory? Do these two variables refer to the same place in memory? And the answer is no. I have two different persons here. They're really different, and so that the answer is false. Okay. And this is the same question again, except now PM1 and PM2 are not two different things in memory. PM1 is the thing in memory, and PM2 points to exactly the same thing. So this will return true. Are the two equal? That'll be true for the same reason. The equal method will be called. It'll check that the first name of the first one is the same as the first name of the second one, and the last name of the first one is the same as the last name of the second one. Of course they're the same because they're the same object, but then this one will actually return true because these two things really do refer to the same location in memory. Okay, so then things get more exciting. We create a class called musician, which is a subclass of person, so a kind of person. And a musician has not only a first name and a last name, but they also have an instrument. And in Python 2.7, there's a slightly different syntax for doing this, calling a superclass. It's more complicated, like most things in older versions of Python. But it's what I showed you today, calling super.init. So a musician asks, initializes its person, giving it its first name and last name, but then it also stores its instrument. And a musician can also convert itself to a string, and the way it converts itself to a string is to print first name and last name and say what kind of instrument it plays. So here are a person who's assigned to the variable PM1 and a musician who's assigned to the variable PM2. First name Pat, last name Morin, and the musician plays trombone. So if you print these two things, you will see PM1 will be Pat Morin. So that's what will print first, and then because PM1 is a person, and you go back and look at their string method, it just prints their first and last name. And when you print PM2, you'll see Pat Morin, trombone player, because it's calling this string method, because that thing is a musician. Okay. Questions so far? So it just calls the appropriate string method for whichever kind of object you give it. Now, here we set it up the same way, same PM1, same PM2, but now we ask, is PM1 equal to PM2? What do you think? PM1 is a person, PM2 is a musician. Do you think that they're equal? So what is Python? What happens when you ask if two things are equal? Python goes looking for underscore underscore EQ underscore underscore method inside those things. So, and in this case actually, PM1 is on the left-hand side. So the first place Python goes looking for that method is in this class, the person class. And if we go back up to the person class and look at what that method is, well, what does it do? It compares the first names of the two things, and it compares the last names of the two things. In this case, even though they're not the same kind of thing, one is a person and the other is a musician, they're still treated as equal. They have the same first name, they have the same last name, and looking carefully at where the definition of equal comes from, it actually comes from the person class in this case, and so it'll treat them as equal. And this will still return false for the same reason, because PM1 refers to a person object somewhere in memory, PM2 refers to a different musician object somewhere in memory, so it's certainly not referring to exactly the same thing in memory. Okay. All right. So, is that clear-ish? If not, then I recommend, go and copy and paste the code out of this PDF file and play with it till you understand.